Can this one be extra credit also?
No, but I'm hoping to grade it fairly gently, because it is kind of a different sort of engineering. All right, everybody got their homework turned in? Either here or online? Okay, good. So, questions about the homework? I'm eating my healthy lunch.
For question 7, how would you add the delay for the yellow line?
Oh, let's talk about 7 last. 7 is the, like I said, I'm not going to grade that one, but 7 is the trickiest of all of these by far. But I mentioned in the assignment that you can assume there's a 2-second clock coming in, right? So you can use that to move from state to state. But I want to take that one apart carefully. So how about any other questions? Yeah.
What's the difference between putting something in an assigned statement, like as a wire, versus like putting something in an always block and then assigning it? Because I know I was having problems like going back and forth.
So you usually can't put an assigned statement inside an always block.
Right, but doing like a variable and then the arrow, something.
So assign x equals a and b. Right, and so synthesis-wise, it's going to make an AND gate, connect A and B to the inputs, connect the output to X. Okay, an always block, and I don't know, let's just do pause edge clock. What that's going to do is take A and B, probably feed that into a D flip-flop, take the output, call that X, connect the clock to clock. So now, at the positive edge of the clock, X is given the value of A and B, right? And if A and B change but the clock doesn't tick, X doesn't change. Here, as soon as A changes or B changes, X is going to change because it's connected to the output of this AND gate that's being driven directly by A and B. So this is a case where X would have to be a register, right? And it's probably going to be the output of a flip-flop. And there's times when that's what you want to have happen, but there's times when you just want a simple gate. Now the other option, which we didn't really talk about, but you can do something like this. Always at A comma B. X is assigned A and B. And that's going to do something like, and I don't know if it actually synthesizes like this. But logically, here's the effect. This always at A, B says whenever A changes or B changes, right? So no, it's not really an OR gate. There's something else here, something magical. But the meaning of this Verilog over here is if A changes or B changes, I want to set X equal to the AND of A and B, right? And logically, that's exactly the same thing as just a plain old AND gate. Because what does this thing do? It says whenever A changes or B changes, change the value of X to be the AND. And a good synthesizer will probably turn this directly into just an assign statement, right? Just a plain old AND gate. But usually, when we talk about always, we're trying to tick on a clock edge, right? We're trying to do something that's synchronous, so it has flip-flops, and we toggle all our flip-flops at the same time, so we usually always on a clock edge. And you can have multiple blocks of code, multiple always blocks that each fire on the positive edge. As long as they don't contradict each other, it should synthesize fine. And sometimes it's useful to think about your Verilog in terms of what it actually looks like in hardware. Sometimes it's useful not to do that, to really just be thinking about Verilog. In the same way that when you write C code, sometimes it's useful to think about what that C code translates to in assembly language. And sometimes it's useful to ignore that and just think about C code. But if you've done 121 and you talked about pointers or addresses of variables, those are things where it's really useful if you can think about these things in terms of assembly language. Engineering 270, we do all that, right? And that can actually help you understand what's going on in C. So same thing with Verilog. Sometimes the synthesis picture actually helps us, sometimes not. Other questions?
For the SR latch,
Mm-hmm.
flip-flop that we made, what were we supposed to set the output to for 1-1?
Oh.
SNR equal 1.
So let's see.
Forbidden state.
Well, it's your circuit. I'd say you get to make it up yourself. Long as you specify, right, and you could say, you know, it's undefined and then not bother saying what happens in that state. Or you could say it's always going to act like an S or whatever. It's up to you. Were people successful with doing flip-flops in Verilog? So the solve problem does some fancy stuff in here, right? And it does it at the positive edge of a clock, so it sets Q equal to all this stuff. But what's an SR really do? So if 0, 0, it's just Q, 0, 1 is a 0, 1, 0 is a 1. 1, 1, I don't know, what do you want to make 1, 1? 0, 1?
Not Q.
Or not Q, that would be a JK.
0.
Let's make it a 0, right? So, so the engineering trick, technically, right, this implements an SR flip-flop, right, which just happens to have this peculiar behavior when both your inputs are 1. So, I mean, you could get away with saying, well, that's really just an SR. But suppose we wanted to actually do this. And is this negative edge triggered? Positive edge. So, right, and you gotta use the keyword module, you gotta define your inputs, which are SR and clock, you gotta define your output, which is Q. All that kind of boilerplate stuff goes up in the beginning. But the always block, so I mean you could do this as a bunch of if statements. if S is 0 and R is 1, set Q equal to 0. If S is 1 and R is 0, set Q equal to 1. If S is 1 and Q is 1, or S is 1 and R is 1, set Q to 0. And we don't have to say what to do if S is 0 and R is 0 because we're not going to do anything. Q is just going to be the same. Or you could go a little bit fancier and do some simplification on this and say, you know, anytime that R is 1, I want my output to be a 0. And if S is 1 and R is not 1, I want my output to be a 1. Otherwise, I don't want to do anything. So you could code this as something like if R equals 1, then Q is a 0. Else, if R is not 1, see if S is 1. If S equals 1, set Q to 1. Or you can write this as an expression like was done for the JK, which would be something like write an equation for Q. Q plus equals, how did he do that with a sign? Oh, using the current. S bar, R bar, Q, or S, R bar. So there's a variety of ways to do that. How's the shift register coming along in the lab? Experiment 4. Want to talk about shift registers? Yeah.
I do have a question. So I noticed that when I was trying to initialize an output, like output 4 bits. I noticed that like when I did output, when I typed in output out, for example, then I did register 30 out. It gave me an error, but when I did output register 30 out, it didn't. So like I was just wondering if like there's a proper way to kind of initialize.
Whatever works. So I'm a lazy engineer. So if I find a way to do something, chances are I'll still be doing it that way the next week. So for example, output register bracket dimensions name seems to work, right? So chances are that's how I'm always going to write it. Because when I sit down to write Verilog, I always have like a sample of my old code that does input, output, register, wire, always block, if then else, right? And you know, the stuff in here should work. I think I got the typos out, right? So you can use that as a template. There's other things that will work, okay? But I don't necessarily know all the other things that will work. And good news is you don't need to. You only need to know a way that works. And if you do this for a living, right, and you make really good money as a Verilog designer, by the way. If you do this for a living, right, then you get the Verilog manual and you find all the details, and after you get tired of constantly saying, you know, if reset, begin, end, and you want a better way to do it, you can find a better way to do it. So yeah, if you got it to work like that, right, it's a good way to do it. But there are other ways. And I thought just saying output outputs and then later on saying register 10 outputs would work. But nuances. Let's talk about shift registers. All right, so what is a shift register? And the shift register experiment is an important one because you need it to make experiment 5 work, which is the 5 of 16 event detector. So the 5 of 16 make a 16-bit shift register. Every time you have an input, the clock ticks, shift it in. That shift register holds your last 16 input values. And the whole purpose of the 5 of 16 circuit is say, hey, let me know if 5 of the last 16 inputs were 1. Well, you've got the last 16 inputs in your shift register, so all you have to do is add one more piece of code which says, count up how many 1s there are in my shift register. If there's exactly 5, make my output 1. And that's a simple but kind of long single line of Verilog code to do that. You can basically add up all 16 values in the shift register. If the sum is equal to 5, you know you had 5 1s, because everything in there is either a 1 or a 0. So the whole trick to experiment 5 really comes down to just building a big shift register. So how many people know what a bucket brigade is? So what's a bucket brigade?
You have a line of people, there's like a fire, you grab water.
Yeah.
Pass it down,
Yeah.
the bucket passes.
So this is how you fight fires if you don't have a fire truck handy or a hydrant, right? You have a line of people, you have a bunch of buckets. Over on one end you've got a source of water, at the other end you've got a fire. So the first person fills their bucket with water, hands it to the next person. While that person is handing it to the third person, first person is filling the next bucket with water, handing it to the second person. And so each clock of the tick, right, which is however long it takes to do each of these things, another bucket gets filled with water, handed down. After 16 ticks, the 16th person now has a bucket in their hand with water, and they splash it on the fire, right? The next clock tick, they're going to get another bucket in their hands and they splash that. So now every clock tick, you've got another bucket of water going on the fire. If this person stops for a moment and the next clock tick, their bucket is empty, right? Now you've got a 0 going down the shift register. And when that gets to the end of the shift register, now the person throws an empty bucket on the fire, right? So that's what a shift register is. It's a bucket brigade. And they use that terminology in some of the data sheets. So what does this look like? So basically, here's our buckets, which are going to be something like flip-flops, right? And something goes into the first bucket, and at the same time, whatever's here goes into the second. So maybe these are the people holding the buckets instead of the actual buckets. So we'll make them square-shaped people. And this shifting happens on the tick of a clock. So your clock feeds, you know, the clock input on all of these devices. And each of these has an input. So this is input 0, this is out 0, this is also input 1, which is output 1, and so on. And so the Verilog code for this is pretty straightforward. It's easier than drawing the picture. So at the positive edge of the clock, what do we want to do? Well, we have a bunch of registers, and we can make this thing an array, right? Register 15:0. We'll just call it shift reg. And so when the clock ticks, well, this is, so let me back up. These arrays of things, yeah.
I can't figure out, what is the reg of 15, what is the 15 reg?
Yeah, that's what I just was about to back up and say. So when you say something like register 3:0, blah, right? Or wire 3:0, blah. What you're doing is making what's called an array. Okay, or maybe a bus. But this says that I actually have not just one variable blah, I have the following variables. I have blah, bracket 0, bracket 1, bracket 2, and bracket 3. Okay, this is a programming concept that we call an array. This says I want blah to be an array of registers with an index, right, a number I can use to pick off each individual element of this array going from 3 to 0. So this is actually like 4 little single bit registers. That's 1, that's 1, that's 1, that's 1. But collectively, we can think of this as a 4-bit register. It's a thing that holds 4 bits. And if we just think of blah, right, that's like a 4-bit number. Or we can think of it as 4 individual bits that all have basically the same name, but they have this extra thing at the end to pick out which bit we're talking about. And we don't need to do that. We could call our registers A, B, C, D, E, F, G, right? But then our code's going to look kind of weird because we're going to say, you know, assign F to G and assign G to H and so on. If you use a register like this, our code's going to look a little more meaningful. So if we think of this as shift reg bracket 0, shift reg bracket 1, and so on, then how do we perform the shifting operation? So at the positive edge of the clock, we want to do the following. We want to take element 1 and assign that from element 0. And we want to take element 2 and assign that from element 1. And so on. So let me do that more cleanly in code. So let's have an input and a clock and an output. So let's make a shift register U1. So we'll toggle our clock every 10 nanoseconds. What is this called? Shift. Alright, so we'll initialize the clock to 0 and the input to 0, and let's just go ahead and wait 50 nanoseconds and then set the input to 1 and then wait for another 40 nanoseconds and then set the input to 0. And let's wait for 80 nanoseconds and then set the input to 1. Actually, let's wait 30 nanoseconds. And then let's wait, what is my clock anyway? 10:20. So let's wait 300. So this is a test bed, right? So the clock's ticking and I set my input to 0 and I'll wait a while and raise it to 1. I'll wait a while, drop it back to 0. And we just want to see what this module does. So let's make a simple shift register. Let me just call this shift. So here's our module shift. Make a 16-bit. All right, I'm just going to call my shift register data. I'm going to find my cheat sheet of syntax. Always chat. Yeah.
So do you need to define data in the module, or have it in the variables list, or no?
It's not an input or an output to the module, so I don't need it up here, right? But I do need to specify right here that it's a register. All right, so no semicolon there. All right, so so what happens when the clock ticks? Register bracket 0 takes whatever value is on the input. Register 1 takes whatever value was in register 0. A lot faster than wiring up a breadboard. So we have 16 crazy assignment statements, right? Which basically say when the clock ticks, take the previous bit's value and copy that into the next bit. Right? And this should work like a shift register. So register 0 comes from in. That should be the end of our block, no semicolon. And let's just set our output equal to bit 15 in our register. I said I was going to call it data. I called it reg. Okay, data. Does that look reasonable? Yeah.
So what I could instead to make it like so you guys repeatedly do the same command or
Yeah, you can do some things. So you could put a loop in there, but I don't want to write a for loop in here. Because once you write a for loop, you start thinking programming language. So I'm gonna, and if you get paid per line of code, this is the way to go. All right, anything else we need? We got our end, we've got an assign, we've got an end module, no semicolon. I'm fairly comfortable with this. I'm gonna guess a 75% chance that it works.
The whole not having to have the data inside of the module statement. So is it only when you have registers to do that?
No, so when we say module shift in clock out, right? What we're really doing is we're specifying a system diagram. We're saying what are the inputs and outputs on this module, right? It's called shift. And we're not saying in that parentheses which one's an input or an output, but we're saying there's 3 connection points to this module, in, clock, and out, right? So we're saying this. Here's a module. It's called clock, or shift. And it has 3 connection points, in, clock, out. Right, the module statement is defining this part of our system diagram. In the next lines where we say in is an input, clock's an input, wire, out is an output, right, that's when we're fully specifying our system diagram. The fact that there's a 16-bit register named data inside here comes up later, right? And we can have a lot of variables, register data, wire, X, Y, Z, whatever, inside this module, but not named in the actual module statement. So the only thing that goes up here are the things that we're going to connect to from the outside world. In this case, from the test bench, when we say make a U1, which is a shift register, and connect our in clock out to those ports. Yeah?
So when you're calling another module, you do like the name of the module and like U1 and the variable assignment.
Mm-hmm.
How are those not inputs to the module? Like say in this one you want to take reg and put it into another, like maybe a test bed. Why would that not be an input to the system?
So it is an input, right? If I wanted to use reg up here, right, then I would need to specify reg in that module statement.
But I'm just not understanding why you don't have to put it up in the module test bed.
Right here?
Block. No, up in the.
Up here? Because
high. Yeah.
because my test bed doesn't know anything about reg or data, right? It's inside the module, but it's, you know, you've got some sort of logic in here, and you've got this, and you've got this, and maybe this over here feeds your output, right? Well, right here, there's an internal point in my circuit, right? But it's not fed from the outside, it's not sent to the outside, it's purely internal. So even if I had a name for this, right, X2, that's not going to show up in the module declaration. The only thing I have to put in there is things that I want to connect to. Now I could put it in there and simply not, you know, care about it. But that's really naming the inputs and outputs to your module. And even though it's got a value inside here, I'm not trying to send that out of this black box, right? It's part of what's inside that you don't see the details of. All right, well, let's generate some syntax errors. Yeah, that's not bad. So register clock, I already said register clock up top. Okay. Wow, that's scary. Okay. Which does not mean it's going to work. But let's see what it did do. So here's the clock. Here's the input. Here's the output. Oh, I only made the output a single wire. I should have made it a bus. So in my test bed, right? Because, oh no. Okay, so after that whole conversation about data, actually I do want to expose that register because I want to actually look at it in the test bed. So, but let's do this without first. All right, so the input goes high right here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 clock ticks later, the output went high. And it stayed high for 1, 2 clock ticks, and the input was high for 1, 2 clock ticks. So this is doing what the shift register should do, right? It's taking the input, and 16 clock ticks later, it's appearing on the output. But you're absolutely right. We do want to look at that data register to actually see how this is working, especially if it didn't happen to work. So let's go ahead and expose that. That data register. So now in the module we do want to say we'll have data, and we'll make that an output. Ooh. Did not like that. Scalar port data has a vector net declaration. You might just say, take a break. All right, yeah, let's take a 5-minute break. I'll figure this out.